In part 2 of this video series, we are going to use a new strategy to approach the same reaction, and we're also going to be balancing in basic conditions instead of acidic. So I want you to see the similarities and the differences between these two methods of balancing redox reactions. Pick whichever one works for you because there are definitely pros and cons of each of them. This one in particular, what it will require is an understanding of oxidation numbers and seeing how changes in oxidation numbers can be balanced simply by looking at the skeletal equation first and then attacking the balancing of the oxygens and the hydrogens from there. So let's just jump right in, and hopefully you will see how this version unfolds. So the first thing that we want to do is we want to identify the oxidation numbers of everything that's not oxygen or hydrogen. And one thing that will be kind of necessary here is the understanding that if we do have a hydrogen, that's going to be +1, and there are examples of it being -1, with the main examples being hydrides, but we're not going to see that in this particular question. And similarly with oxygen, those are going to have an oxidation number of -2, and of course you will see the -1, but not in this example. You're going to see those most often in peroxides, and you're even going to see other oxidation states, things like superoxides, but beside the point here. So what this strategy does is attacks the electrochemistry first, and so we are looking at the oxidation numbers, we're going to balance the electrons, and then we're going to go back and balance the oxygens and hydrogens and create those basic conditions. So we do need to identify the oxidation states of everything in this skeletal equation. So we're going to start with MnO4-, and what we're going to do is we're going to say we have 4 times -2, and that added to whatever the oxidation state of manganese is going to have to equal that -1 overall charge that you see right here. And the way I approach it is simply to say -1 is equal to what plus -8? And the answer would be +7. Now going over here all the way to the right, we see this MnO2 is 2 times -2. So what plus -4 is going to get me 0? Well, that should just be +4. So we're going to do the same thing for the other half reaction, where we simply look at this and we say 2 times -2 plus what gives me -1, and I say, well, that's got to be +3, because +3 plus -4 gives me -1. And then over here on the far right, I have 3 times -2 plus what gives me -1. Well, that's got to be +5. And so now we can look at these oxidation numbers and say, well, for this particular half reaction, we went from a +3 to +4. That's a -3 change in the oxidation number. So that means we gained 3 electrons. Now up top, we ended up going from +3 to +5, and so we had to have lost 2 electrons. And I don't really care about showing the oxidation and reduction here. Really what I'm concerned with is the number of electrons that are transferred. Now, similar to our strategy in part 1, we do need to understand that this change in electrons needs to be the same on the left and the right. And so for this process and this process, we need to have the same number of electrons. And so in order to do this, I'm going to multiply the manganese half reaction by 2. And then I'm going to multiply the nitrogen's half reaction by 3. Now what that does is create 6 electrons overall transferred in each half reaction. But what we haven't done yet is applied those basic conditions. So I'm going to take the 2 MnO4- plus 3 NO2- goes to 2 MnO2 plus 3 NO3-. And I'm going to look at this and say that this is actually balanced based on the transfer of electrons, but I haven't actually balanced the chemistry of those basic conditions. So now I'm just going to do my typical strategy of balancing oxygens with water, balancing hydrogens with my protons, and then creating those basic conditions. So let's take a look at how we do that. So over here on the left, we have a total of 8 plus 6 oxygens, which is going to give us a total of 14. Over here on the right, we have a total of 4 plus 9 oxygens, which gives us a total of 13. What that means is we need to add 1 water here on the right. What we did here is we created an imbalance of hydrogens, and so we're going to go jump over to the other side of the equation and add 2H plus. And this would actually be my answer if I were dealing with acidic conditions, but I'm not. I'm dealing with basic conditions. And so what I have to do here is I have to neutralize the H plus with hydroxide, but because my reaction is already balanced, I need to understand that if I were to just simply add 2 hydroxide to the left side of the equation, my reaction would no longer be balanced on the left and the right. And so I do need to, in this particular step, add my hydroxide to both sides. And what I end up with is 2H2O plus all my original stuff plus that water that remains and those 2 hydroxide. And this is getting pretty close. The only other thing that I need to recognize here is that I do have 1 water on the right and 2 on the left. And so I'm just going to make up for that by getting rid of 1 here and then getting rid of this entirely. And so I'm going to move this hydroxide over. And so the last step is to check the charge balance. And so I see that I have a 0 right here, a -2 right here, -3. That gives me a grand total of -5. And then I have 0 right here, -3, -2. I get -5, and then I get my check mark for charge balance. So you see that this strategy really took a lot more thought, but it is definitely a viable option if you're very comfortable with oxidation states. And as you progress and understand the role of stoichiometry in balancing those electrons in your redox reaction, this definitely becomes a sensible solution to balancing these particular reactions.